And last time we saw this notion of a complexity class. So we said that class P, which is a set of all problems that can be solved in polynomial time. And remember, we've restricted our attention to decision problems. We said that generically you can reduce optimization problems to decision problems. So from the point of view of complexity, people usually think about decision problems. And class P is a set of all decision problems that can be solved in polynomial time. And these are like a couple of simple examples that we have seen through the course. And yeah, so the class NP, which we defined last time, is all decision problems for which you have a verification procedure. And yeah, so an example that we saw is this thing where consider this decision problem where your input consists of a graph and some number k, and you want to ask, does this graph have an independent set of size at least k, size k or size at least. And this problem we said is one of the canonical examples of NP, and for this a verification oracle, a verification algorithm will basically expect as input the independent set, and it will just verify that it is actually an independent set. And we saw this picture of a two-prover game. Okay, so you have this prover, you don't care how the prover works, it's some magician who provides some witness. Okay. And the verifier is just some simple algorithm, it's a polynomial time algorithm. Okay. And both of them have access to this instance I. And the goal of the prover is to provide some witness or certificate. So this person provides the certificate W. And the verifier, all it does is it runs some verification algorithm, which I call ALG, on the instance I and this certificate W. Okay. And it either outputs yes or no. It either accepts that certificate as a valid certificate for this input or no. Okay. And the goal of the prover is to convince the verifier to say yes. Okay. And we said that that is a correct verification algorithm if you have this property, these two properties. If I is indeed a yes instance, then there has to exist some witness W that will convince this verifier that this is a yes instance. And if I is actually a no instance, then there is no way, then there should be no way that the prover can fool the verifier into accepting. And we saw this in the example of the independent set. Right? Because in the independent set, the verifier was this very simple algorithm that just took the set of vertices, verified that this is actually some subset of the vertices, and verified that this is actually an independent set and it has size at least k. Now there's no way, if the graph really does not have an independent set, there's no way somebody could convince you, could convince this algorithm that there is an independent set. Because it has to provide some set, and if there are edges, there's no way to connect. Okay. So any questions on this? Because this is a very important thing that you should understand. Yeah.
So both prover and verifier have some complexities, right?
Yes. So the prover's complexity we don't care about. All we care about is that the verifier should run in polynomial time.
So my question is that if the prover, the complexity of prover is polynomial, and the complexity of the verifier is also polynomial, then the problem is in the class of P.
Exactly. Yeah.
If the verifier is in the polynomial time, but prover is exponential, then this is in the class of NP.
Well, the prover need not, in principle, even be restricted to exponential. They could do anything you want. Okay. But yeah, in most cases, there's no point in being much worse than exponential, because in exponential time you can actually try all possible things. Sorry?
I mean, it's not in polynomial time.
Yeah.
Not polynomial. So if none of them are in the polynomial time, then the problem is neither P or NP, right?
So if yeah, so this whole framework makes sense only if you restrict the verifier Okay? If the verifier is all powerful, then the verifier can actually compute the answer to the problem, right? So then the prover becomes redundant. So suppose you allow the verifier to be exponential time, then the verifier can actually compute the true answer for the instance. If the true answer is yes, he'll say yes. He'll totally ignore the input of the prover. If the true answer is yes, they will say yes. Otherwise, they will say no. Then no, whatever the prover does is irrelevant because it's not even being looked at.
So we had three classes, right? Class of P, class of NP, and the complement of class of NP.
So that's a different, yeah. So what he's asking is, right, we had a picture last time. I don't think I have the picture, but yeah, so you have the class P, which we believe to be a strict subset of the class NP. Okay? And you have everything outside NP, sure.
So I want to know the definition of the complement of the NP. What's the definition for P and NP?
So you're not happy with the definition that it's the complement of NP?
So I want to know what happens for prover and verifier if it is a complement of NP.
Yeah. So I mean, I don't think you can. I mean, the only way you can define it is that there is no system like this, right? So I mean, because yeah, it's like saying it's very yeah. Often you cannot define the complement of a set in the same way you define the set itself, right?
So the way that I said that both of them are not in polynomial time is not accurate.
No. Yeah, that's not accurate. Yeah, good question though. Yeah.
What was the difference between the instance of a problem and the solution?
So yeah, so the canonical thing you should think of is the graph itself. In an independent set example, is the instance. Okay, and the witness here would be an independent set of size k. Okay, and there's also the number k. Witness is some subset of vertices of size at least. And this witness would be accepted by the verification algorithm if it is indeed a subset of the vertices of size at least k and it's an independent. Yeah.
So really the witness is much like a possible solution to the instance.
Yeah. So the witness is basically a solution that the verifier can actually check that okay, this is a valid solution.
Okay.
So the verification algorithm is often just is it a valid solution? Okay. So this is why in homework 6 I have one problem about this, and you should try to solve it because I mean this is a concept that you you should understand. So right. So yeah. So it might seem a bit simple, and sometimes it might seem a bit silly, but it is actually non-trivial to once you actually understand what's going on, right? Because the verifier is basically checking that the solution is correct. But the important thing is that the verifier should not. That you should not be able to fool the verifier into saying yes when the true answer is no, and that's very important.
So
yeah.
If the question is about the decision problem, so the instance of the decision problem includes the witness too, or not?
This is an instance of the G is the instance of the decision problem. So the instance is available to both.
Yeah, I know, but when you are saying that for the instance of problem is just G for example, of V and E,
and also the K because it's a decision problem. Yeah.
For division problem, we should say that witness is a part of the problem, or
No, witness is not part of the problem, right? So the witness is the set of vertices.
what is the rest?
this is the right independent set. So, I mean, so imagine you could also imagine one way of thinking about it is verifier is somebody who actually wants to solve the problem, and they're getting some help from an all-powerful oracle. Okay, and what they are able to do is, if this person gives a correct witness, they are able to produce a solution. So one way of thinking about it, though it's not precisely right, I mean, in the sense that they don't have to be able to compute this, but still.
So I think his question is that if the answer of the problem is yes and no, so for example, prover provides an algorithm and the result of that is yes and no. And the
What do you mean is yes and no?
Because it's a decision problem, right?
Okay, but the answer is either yes or no, right?
Yes.
Okay.
Okay.
Yeah.
So the prover says yes and no, and the verifier should again say yes and no. Do you get what I'm saying?
So you're saying that the prover should be able to convince. So prover you are thinking of as like an algorithm that actually solves the problem, and they should be able to convince the verifier that what they have computed is the right one. Is that what you're trying to say?
So what I'm saying that if it's an optimization problem,
Okay.
then it makes sense. We get an instance of the problem, possible solution, get to the verifier and verify it and say, okay, this is correct or not.
Yeah, but in an optimization, we've already reduced to a decision version. Okay, so let's forget about optimization for now. It is a decision problem. Now the goal is so the prover's sole goal is to make the verifier say yes. Okay, and what the definition of NP basically says that if the instance is actually a yes instance, then yes, they can provide a witness such that the output will be yes. Otherwise, there is no way you can make it. Yeah, there was another question. Yeah.
So just to verify, if there's no polynomial time verifier for the decision problem, then it's neither NP or NP.
Yeah, it's not. This is not it. And one example you can think of, maybe this is something I referred to last time, right? It is that imagine your problem is checking if a number is prime. So, so for this there are witnesses, but it's a non-trivial witness, right? So suppose you are given some number n, which has some little n digits, and this is your instance, and now you have the prover and you have a verifier. Verifier is some algorithm, and this takes as input n and some witness, and it's supposed to say yes if the number is prime. Supposed to say no if it's complex. Okay. So now, what should the W be, and what should this verifier be, so that both those properties work? It turns out that this is a tricky question to solve. Okay. So the other thing which you will realize if you think about it a little bit is that even if the instance is a yes instance, not all witnesses may actually lead to the algorithm accepting, right? Because even if your graph did have an independent set of size k, maybe the prover gave you an incorrect set, in which case you will still output. So what we are saying is that if it's a yes instance, then there exists a witness term. So these are all small subtleties that you will realize once you start. Yeah.
So with the prime number verifier, you're giving it n, which is the potential prime number.
Yeah.
Is the problem deciding what the witness is going to be for this? I don't understand.
Right. So if you want to prove that this problem is in NP, then you'll have to come up with a verifier. You'll have to say what the witness should be.
And that's the question I'm unclear about.
So for certain problems, it is obvious, right? Like for an independent set, it is obvious what a witness should be. The witness should be the set itself. But for prime numbers, it's not obvious because what should the witness be? So that's a polytime algorithm will be convinced that n is prime given this witness.
Okay.
Right. So yeah, no. In this case, it is non-trivial. So there is something called a Pratt certificate, which is a non-trivial witness for primality.
So could a potential witness be a set of prime numbers that are not?
No,
No?
because that will not convince. I mean, so if you are given a bunch of prime numbers that are not n, that are smaller than n, let's say, maybe you will verify that these guys don't divide n. But as long as this number is small enough, so this is difficult. But on the other hand, if your problem was compositeness, right? So because remember, the witness has to be polynomial size. The verifier has to run in polynomial size.
Okay.
If your problem was so this is problem was check if number is prime. On the other hand, if your problem was check if number is composite,
Then the witness could be the two composite values,
exactly.
and the verifier can.
Right. So here there is a witness, right? Because now the verifier can expect a factorization of n. Okay, and then all the verifier has to do is check that these two factors are smaller than n, and you can just verify their product is actually equal.
Okay.
So this is a nice, yeah. So this I think kind of illustrates the difference. Illustrates what you really need for a problem to solve. Yeah.
So if a problem is given to us and asks us, okay, prove that this is P, NP, or complement of NP. How can I figure it out if this is complement of NP?
You can't. I mean, it's yeah. I mean, you could. I mean, in fact, people took a long time to realize that primes are in NP. Right? Like, yeah. I mean, this was an open question for a while, and sometime in the 70s, people discovered that there is actually a short witness for this. We still don't know if, for example, the complement of SAT, which is the satisfiability problem that we'll see soon, is in NP or not. So
the gain things that you mentioned, so that one, even this is not clear if it is a complement of NP or.
Yeah, we don't know if. I mean, we believe it's not, but we don't know how to prove that there is no witness, right? It's the same problem as showing low bounds.
Oh.
How do you show that there is no clever way of coming up with a verification algorithm? Yeah. All right, good. So this is a definition of NP. Okay. And so the last time we also started looking at reductions, right? So these are much more tangible in the sense that so a reduction is basically informally what you would like to capture is that if problem A reduces to problem B, that means that a polynomial time algorithm for B can be used to obtain a polytime algorithm for A. So in some sense, that's why I write it like this. It delivers the informal notion that A is an easier problem than B. Okay? But there could be like polynomial blow-ups. Okay? So this is how we write it, and we said that the formal definition of this, a polytime reduction from problem A to problem B, is some transformation that maps instances of A to instance of B. Okay? And we said that yes instances map to yes ones and no instances map to no. And we had this picture, basically said, yeah, so these are A, this is problem B. And this transformation T runs in polytime. Okay. And it transforms yes guys to yes and no guys to no. And yeah, this is what I said is important, which is that T has no idea, of course, if a yes instance, I mean, if it's a yes or a no instance, right? Unless the problem happened to be solvable in polynomial time. So typically, the transformation just transforms one instance of problem A to an instance of problem B. And we'll see examples of this where, I mean, this comes naturally in certain contexts. But this is the formal notion of a reduction. Okay, so this is the picture you've got to have in mind. We write it as A.
So does this mean that when you transform instances of A to B, that you're adding information to the instances of A? Or is it just modifying it in such a way that it works with T that is successful with B?
What do you mean by adding? Can you say that again?
I'm just trying to imagine, because the purpose of the verification is T, I'm assuming, correct?
No, so this now has nothing to do with the verification.
Oh, okay.
Yeah, so this is just, so we've moved on from the verification. Now we are just talking about what it means to reduce one problem to the other. Yeah, so there was, yeah.
And this definition includes like yes instance mapping to yes instance and no instance mapping to no instance. Like, it can just be some arbitrary mistake.
No, it should be a fixed mapping. I mean, it should be something where you give it some instance, it produces some fixed instance. But the point is that it should only transform yes once to yes and no once to no. Yeah.
Is a reduction reversible? Can we?
Oh no. In general, not. Okay. Like in fact, that will motivate our next definitions. Okay. So once you have the notions of reduction. Okay, so now you can define what NP hard and NP complete are. Okay. So what is so if you have a problem A, you call the problem NP hard if a specific problem, which I haven't defined so far, but it's called Boolean satisfiability. If this problem reduces to A, and for now you can also think of it as independent set reduces to A. Okay, so there is a certain problem called Boolean sat. Okay, and you can replace this by independent set if you want. This has some yes instances and it has some no instances. And if there is a transformation T such that you, and this is problem C. So if there's a transformation like we saw before that reduces Boolean sat to your problem, then A is said to be NP hard. And so remember, this is like saying that Boolean sat is in some sense easier than problem A. Right? So this is why I introduced this notation. So that's why, so this is like intuitively how you, it's a problem that is harder than Boolean sat. Okay? And that is intuitively why we call it NP hard. So now, hopefully this notation makes sense and it lets you appreciate the difference. And you call the problem NP complete if, like you were saying, there are transformations in both directions. So if there is a transformation, if firstly it is NP hard, and there's also a reduction from problem A to Boolean sat. Okay. So if both of these happen, then you call the problem NP complete. Okay. So this is effectively like saying that these two problems are equally difficult. Okay. So if a problem is as hard as Boolean sat, informally speaking, you say that it is NP complete.
Can you say, for example, NP complete is an optimization problem, NP hard is a decision problem?
No, both are referring to decision problems. Okay. So throughout we are referring to NP to decision problems. And we would like, NP hard can include problems that are strictly harder than Boolean sat, like games and so on. NP complete are problems where they are equally hard, so things like independent set fall into NP complete. So, So these can be like super hard. Can be like super hard. So problems that are like some p-space complete or whatever can all be considered NP hard because they are much harder than Boolean SAT. While NP complete is problems that are the same kind. Yeah.
Travis spells right?
Yes.
So, does this take into account all of the clever tricks you can use, like branching down and whatnot? Like, or does it just assume some sort of brute force?
No, so that's the nice thing. So far everything we've discussed is very algorithm of what do you call it? Agnostic. Yeah. I was thinking of obnoxious there. Okay. So yeah, so it's totally agnostic to algorithm, right? Because yeah. So if you can, so what it's essentially saying is that if you have clever heuristics for traveling salesmen, you could potentially use it to get clever heuristics for Boolean SAT. Okay? Because there is a reduction from Boolean SAT to traveling salesman. So if there is a clever algorithm that can solve that efficiently, then you can also solve this one efficiently. Okay? That's what it's. That's how you should think of reduction. So likewise with I told you during our optimization discussions that there are lots of good heuristics for integer linear programs. So it turns out integer linear programming is also NP hard. So you can actually reduce Boolean satisfiability to ILPs, and you can use ILP solvers that do fairly well in practice. And so you get pretty good algorithms for things like Boolean satisfiability. Okay. So heuristics also translate just because, and that's the nice thing about this definition, because you are reducing instances of one. You're transforming instances of one problem to instances of the other problem. So it shows an equivalence in this sense. Yeah.
About this transformation, it's definitely a computable function, but we don't know if it's polynomial time or.
No, it has to be polynomial time. So the transformation function has to be efficient and it should run in polynomial time. And this is very important because, and it should preferably not blow up the instance too much. We allow a lot of slack, but if there is a transformation that takes time n to the 100, it's strictly polynomial, but it's somewhat useful. Okay, so, yeah. So yeah, these are all very good questions. Anything else? Yeah.
That Boolean satisfiability problem, is that a polynomial problem?
No. I mean, we don't expect it to be.
Okay.
Yeah. So I will define the problem in a little bit. But it's you can also think of it as replace it by independent set, and the same thing holds. Yeah. So the nice thing about NP complete, about this class of NP complete problems, is that because they are both reducible to and from Boolean SAT, you can basically reduce the problems to and from one another. Because you can think of using Boolean SAT as an intermediate and say that, oh, okay, I can reduce one problem to the other. Okay. So we'll see complicated. Alright, so let me start with what Boolean satisfiability is. Okay, so it is, yeah, actually, how many of you have seen the problem before? Many of you have seen it, but let me define it anyway so that becomes clear. So I will define it using a circuit. So some people call this circuit SAT, but it's the same thing. Okay, so suppose you have a Boolean circuit, which means a circuit consisting of AND, or NOT gates. So I'm actually not sure. There are these weird pictures that people used to draw AND or NOT gates, which I don't exactly know. Okay, so yeah, so let's not go there. Let me draw boxes for all of them. So you have gates. So you have AND or NOT type gates. Okay, and so you have various gates, and you have a bunch of inputs. Okay, so let me call the inputs x1, x2, up to xn. Okay. And so these are your inputs, and they go as inputs to your circuit. So maybe one input goes to a bunch of things, bunch of gates, and then there are gates on top of this, like you have some gate over here, and you have something producing this, and you have some NOT gate over here, and produces something, and in the end, they compute some formula. So in the end, there is something, which is the output, which I will call f of x1, x2. Okay. So this is a Boolean circuit. So you have Boolean inputs. So these are true or false. Boolean just means true or false. And these gates are like logical and logical or logical. And the output is some function of these. So the Boolean satisfiability problem basically asks, so given some circuit like this, so the problem is given a circuit F, do there exist inputs x1 through xn such that f of x1 through xn is equal to true? Okay. So the circuit is the input. Okay, so the input consists of the circuit, and you are supposed to tell if there exists x1 through xn such that the output f is true. Okay, so is the problem. And as you can imagine, this is as much of brute force search as clean a definition of brute force search as it comes, right? In the sense that intuitively you have to try basically all possible true-false assignments of the variables. And at least that's what it seems. And is there a good verifier for this problem? Like, what would be a witness to convince somebody that this the formula output is true? Yeah.
A set of inputs that produces true.
Yeah. So this is also an example where a witness is very clear, right? So a witness is just what are the xi's, what are these xi values, so that you get true at the top. And given this witness, one can just simulate the circuit and find out if it is if it really outputs true or not. Okay. So witness from this. Okay, so trivial to see. That Boolean sat is an end. Okay, so here the witness is the assignment. So a satisfying assignment, I guess if you haven't seen the phrase before, is basically the x that makes the formula true. So, and if one such thing exists, then that would itself act as a witness. Yeah.
What's the size of the definition of the size of the problem?
It's the number of gates, inputs, yeah, everything you have. Because this is the instance, so the size of the instance is however much it takes to represent this. So you can think of it in general as like the number of wires plus the number of nodes. Yeah. Yeah.
So can people come up with like empirical intuitions where like they just like programs algorithms and then when it compiles it becomes
circuit is required to make the program.
Oh, what do you mean? What kind of circuit was required?
So like I write something in Python, eventually it compiles,
Okay.
simple command or not gates.
Okay.
So say I have no idea about whether something's in hard, can I empirically start to get an idea by checking a few?
So you have the circuit or you don't? You have the circuit.
Well, if I can program it in Python, I have the circuit.
Okay. So you have the circuit. And what's your question? You want to know if
Can people like empirically start to get an idea of something has this Boolean satisfiability?
if this is satisfiable or not by
Just letting the computer make it.
no, right? Because it's what is, I mean, are you saying that now there is some structure to this? I don't understand your question again. In the sense that it's, yeah, if you have a circuit and then it's basically the satisfiability problem you're asking.
I think it is the other way around. You have to find the value for the inputs of the gate.
Right, you've got to know what
Now
is
find
X
the
and-
tip gate that is satisfiable or not. You can have any tip gate. Now the question is that what is the value for the input of the tip gate that makes it satisfiable?
Oh yeah, maybe that's what you're confused by. Because we are asking, I mean, you are given a circuit. This is just some function of x1 through xn. Okay? And you want to know if there exists some values for x1 through xn so that this thing would be true. So for arithmetic circuits, for example, it's like asking, there is some polynomial and are there some values, let's say I have some polynomial x squared plus y squared plus 4x plus 1, okay? And then I ask you, are there x and y such that this is equal to 5, right? So it's kind of like that. It's just, but now you have these Boolean variables, and you want to know if there are some values for these Boolean variables, so that the output turns out to be true. Okay? The output is 1. Yeah. So it's some kind of a solving this Boolean function. Right? So that's Boolean satisfiability. And I just told you that Boolean satisfiability is an NP because you can very easily come up with a verification algorithm. And the algorithm just runs, it takes some witness, which is supposed to be a binary assignment, and it runs the circuit on it. Alright, so the first non-trivial theorem about this space is what is called the Cook-Levin theorem. And what it says is that any problem in NP, okay, which basically means any problem for which there is this kind of a verification procedure, okay, has a polytime reduction to Boolean sat. Okay. So maybe I shouldn't say verification algorithm, I should say verification procedure, like we saw before. So what I'd like you guys to understand here is the statement of this theorem. Okay? So it's saying that take any problem in NP. By the definition of NP, it has to have like a verification procedure like we saw. Right? So there is some algorithm that takes a witness, takes the instance, and produces yes or no. And any such problem has a polynomial time reduction to Boolean satisfiability. So that's what this theorem is saying. And in some sense, what that means is that if I take any problem A in NP, so yeah, again I need to start this because it has started to die every half an hour. Sorry for this. I'm glad it's happening at the very end of the semester. I don't have to buy one the next year.
So that just said that since Boolean satisfiability is the hardest problem in NP.
Yeah.
But I thought we said a problem is NP hard if Boolean satisfiability reduces that problem.
Yeah,
Does
yeah.
that mean that every problem in NP is incomplete?
No. I've come to that. Yeah. So, yeah. So what I have written on the slide is that this means that in some sense Boolean satisfiability is the hardest problem in NP, in the sense that the Cook-Levin theorem says that if you have some problem A in NP, then A actually reduces to Boolean satisfiability. So his question is, but we define the problem to be NP hard if Boolean satisfiability reduces to that problem. So the answer to that thing is that, yeah, basically if you have a problem that's NP hard, and if it's also in NP, then it's NP complete. Yep. So, but it may not be in NP, it may not have this kind of a problem. So, yeah. So I will write that down because that's a nice point. Right? So you have some problem A in NP. Like A colon so this is what the Cook-Levin theorem says. And that's, effectively like saying that any problem in NP reduces to this. So Boolean sat is in some sense the hardest problem in NP. So his question was, we defined NP hard and NP complete. So NP hard has all problems A such that, okay, let me stop writing Boolean, let me just write sat. Okay, so sat reduces to A. Okay. And so if a problem is NP hard and it's also in NP, then the Cook-Levin theorem automatically implies that it's NP complete. So yeah, that's the nice. So this is another easy corollary. If a problem is NP hard and it's in NP, because the definition of NP hard means that sat reduces to this. Okay. And Cook-Levin theorem implies that because it's in NP, there is a reduction in the opposite direction, and therefore there are reductions in both directions. Therefore, it is NP. Okay. And so, if you have an NP hard problem that is, that is strictly harder than Boolean sat, then it's actually not an NP. So that's the.
What's the example of that?
That's the games or things like that. At least we believe that that's the example. Yeah, we don't know how to prove it, but yeah. Okay. Yeah, again, I mean, these are slightly subtle things, so I expect that you'll have to go and kind of understand these a little bit. All right, so let me give a sense in which, some idea of the proof of this. So I won't give a formal proof of this theorem, but so is the statement clear? It's just saying that any problem in NP, that is any problem that has a polynomial time verification procedure, can actually be reduced to Boolean. And the hand-wavy proof of this is actually very easy. Okay? So So the proof is like this. Okay, so we know that if a problem is in NP, you have this prover verifier framework, right? So there is some verification algorithm, and verification algorithm takes as input. Let me draw this contour, right? So you have this verification algorithm al. Okay. It takes as input the real input, the instance. Okay. So the instance I. Right. And the witness, and it outputs yes or no. Okay. So if a problem, and let's call this problem the alg sub A. So problem that, I mean, it's an algorithm that depends on the problem A. Okay, and if you want something concrete, think of A as independence. So in this case, the verification algorithm basically takes the graph, and the witness here is like a set of vertices. There's some checks on the size and stuff. So now, what I would like to convince you is that any algorithm that you can reasonably think of is a circuit, right? Because if you think of what any like basic programming, I mean any algorithm does, it's essentially some circuit, right? Like you were saying, like any Python code you can imagine as being a circuit. So you can imagine that this algorithm is now this big circuit. Okay, so it has some AND, OR, and NOT gates. So it has some AND, I think some NOT, stuff like this. And this is taking as input this instance I, which you cannot change. And this witness, there are some bits of the witness. W capital. So the witness consists of a bunch of bits, and it takes the instance I, it takes a bunch of witness bits, and it produces yes or no. Now I'd like to claim that this is basically the reduction. Okay, that this is essentially you have come up with an instance of Boolean satisfiability, because now this is a circuit. Okay. And the variables are now these witness. So the variables are now the W1 to W2, because I is some fixed set of variables. Okay. And so what you're essentially asking is that, oh, okay, if there are some Wi such that this one produces yes, okay, then this is a yes instance. Otherwise, it's a no instance. So you have reduced this problem A for which there was a verification algorithm. So any problem A that has verification algorithm, you have reduced it to 0. So this is the idea of the proof. Okay, so you have to, when you see a formal proof of the Cook-Levin theorem, it will involve often some, I mean, it will often look messy, but this is the rough idea. Okay. And if you believe the fact that any algorithm is basically a circuit, then it's immediate. Okay. So that's Boolean satisfied. Okay. So that's the proof of this Cook-Levin theorem. Yeah.
So perhaps this is an oversimplification, but it seems to be that if you can create a machine that does the algorithm, then that proves that it's NP.
Yeah, so you're saying that if you can solve Boolean satisfiability well, then you're in great shape. Is that what you're saying?
It's just a programmability issue. If you can make the algorithm into something a machine can operate on.
Yeah, but you don't know how to produce W's that will make the circuit output yes, right?
Okay.
That's still a problem. If you can do that, yes. Right. So yeah. So all this did is so this is the nice thing about reductions, right? Like you looked at that algorithm, you came up with a circuit for it, okay? But you have no idea if there were inputs that made that algorithm output yes or not.
It's the transformation of the witnesses to something that can be used in this situation.
Right. It just transformed one instance of one problem to an instance of the other, without really knowing whether it's a yes or a no.
So, then it proves that this is transformable. I mean, the algorithm is repeated.
Yeah. So this, I told you, this is a hand-wavy proof. This is not a. So you have to So formally, what people do is they say that okay, what is an algorithm? An algorithm is basically some set of. It's a Turing machine with a finite control, and then you simulate each operation of the Turing machine with some circuit, and that's why the proof of the Cook-Levin theorem, if you look it up in any book, it will be somewhat long. But I would like, but I just think that this intuition that any algorithm is basically a circuit is the guiding intuition. And if you believe that, then it's basically immediate. Right. Good. So that's all I want to say about the Cook-Levin theorem. And this is what the hint of the proof is, that bits of the witness are the variables and the algorithm itself can be encoded as Boolean. Okay, so next I wanted to show two examples of reductions. Okay. So because this is the last class, this will be somewhat of a dense class. So we'll see a reduction from. Actually, I wanted to show a reduction from that basically shows that independent set is NP complete. Okay. So for that, we'll go through an intermediate problem which is like a simplified version of Boolean satisfiability. So let me define. So the goal for next 15 or so minutes is give a concrete example of a reduction. Okay, and this example will basically be independent set. Because this is a problem we've been looking at for a while, and we would like to say, in fact, I will prove that Boolean sat reduces the following time. And I would also like to show the other way around. So, and I would like to make a general statement that reducing most natural problems to Boolean sat is often easy. Okay. It's the other direction, reducing Boolean sat to your problem of interest, that is often tricky. So this part is usually easy. In this case, we will see why it's easy. Sorry? Yeah, so right. So one thing is observed is that by the Cook-Levin theorem, this is immediate, right? Because I have already told you that independent set is an NP. Okay. So the Cook-Levin theorem automatically implies that it reduces to Boolean sat. Okay. So that's an easy proof. Another proof could be you can even do this directly in this case. Like you can say that I can encode the witness as So you can actually this is actually a good exercise for you to actually prove the Cook-Levin theorem for this example. Okay. So you can actually say that, okay, I know what the witness is supposed to be, some subset of the vertices. Subset of the vertices can be encoded as a binary string. And how would a verification procedure work on this plan? So you've got to come up with a circuit that essentially accepts this string if there are at least k ones, and if between any two vertices that have a 1, there is no edge. So this is yeah. So this also follows from So this is a simple exercise for you. Again, it's not a terribly important thing for you to do, but if you like to understand these things, this is a simple example. So any question on this second part? So we'll do most of our focus on the first part. Okay, so that will be the goal for the next step. Yeah.
Couldn't understand the proof you said without using Cook-Levin.
Oh, I was just saying that. Okay. So I guess his question is, can you give a direct proof of this? Okay, and I was just saying that. So what does it mean to show that independent set reduces to Boolean set? Like you have to take an instance of independent set. So you have to take some v comma e and some k and produce a circle, right? And I was saying that, and yeah, so here we know that the witness is a subset of vertex. So you can use this intuition to come up with a circuit that basically has as inputs some x1, x2 up to xn. So these are supposed to be Boolean, 0/1. Okay. And these are supposed to be 1 if the witness contained this vertex. Okay. Like xi is 1 if I is contained in the witness or not. And you can think of this circuit as having two pieces. One piece checks if sum over I xi is more than equal to k. So this gets as input all of these things. This is one piece of the circuit. Another piece does this thing where for every edge you have one block. Okay. And this one, let's say this is edge ij. This has as input this xi and xj. And this is some small circuit that if both of them are 1, then it outputs a false. Because you don't want both of them to be 1 if this is an edge. Right? So, yeah, this is something which outputs a false. And then on top of it, you just have an AND of all of these. So this is the circuit. And you can verify that this circuit actually.
Yeah, if you said xi equal to 1 means xi belongs
To the independent. Yeah.
But here you said xi and xa are equal to 1, then
It outputs false. Yeah. Yeah. So I mean, if
We have an exit.
no. So you want the independent set to not have any edges, right? So if you gave a set where where both of them were 1 and there was an edge, okay, then this is not a valid set. Anyway, this is an exercise, so let's not waste too much time on this. Okay, so this is a technicality. It's about it's manually constructing a circuit, which you know you can do if you try hard. Yeah.
I guess I've just been thinking about like how correctness, like how like the correctness of the original algorithm fits into this. So if we know that the set of B and E is like a correct like formulation given that algorithm, how is that different than I guess like the witness?
Oh, so the original algorithm for the problem has nothing to do with this, right? Because the witness, I mean, a verification procedure is not trying to give you an algorithm. It's just trying to take, imagine you're trying to convince someone this is a yes answer. Yeah. And the main thing about a verification procedure is that it must not accept a false instance. Must not, if your instance was actually a no instance, there's no way somebody should be able to convince you that it's a yes. And that's what you'll have to prove when you show the correctness of the reduction. Yeah, and in general, the tricky thing when we show the correctness of a reduction will be this showing that a yes instance always maps to a yes instance and a no instance always maps to a no instance. Okay, so that will be the tricky thing that you have to say. Alright, so with that said, let me try to focus on this. So we want to show that Boolean satisfiability reduces to independence. Because this is the kind of a reduction that we've not seen so far. So, good. So first I'm going to come up with a simpler form of Boolean satisfiability, which I will call 3-sat. So this is a special case of Boolean sat. And this problem is as follows. Okay, so here you have variables x1 to xn. So these are variables, Boolean variables. And you have a bunch of clauses. Okay, so clauses, M clauses. What does this mean? Clause I has I will also denote it by CI. This is a small formula. This is an OR of 3 of these things. Okay, so that's why it's called 3-sat. So this is xi or xj bar or xj. It looks like this. Okay, so it involves 3 of the original variables, potentially with negations. Okay. Xj bar is like the logical negation of xj. Like if xj is true, xj bar is false, and so on. Okay. So every clause looks like this. Okay. So it involves exactly 3. Exactly 3 variables. And it's the OR of those. So this symbol is the OR. If you remember, we saw this in the union bound stuff. It's like logical OR. And 3 variables or their relation. So each clause is like this small formula, which is just an OR of these 3 things. And the overall circuit, the overall formula which I will call phi, is C1 and C2 and C3. Okay. So you have M clauses. The ith clause looks like this. It has some, the i's actually. So this is not the same I. XL. All I'm saying is that each clause is the OR of 3 of these variables or their negation. Okay. And the overall formula phi is just an AND of this. And this corresponds to like a very simple circuit where you have, it's like a 2-layer circuit. So you have one gate for each of these clauses. To CM, and each of these guys gets 3 inputs, probably with some negations. And your final thing is just this giant AND gate. Okay. So this is a special circuit. And the question is, and the 3-sat problem basically asks, are there values for x1 through xm so that this circuit outputs yes? Okay. The question is, are there xm such that p is true? So is this question here? Any questions? So you should get 2 things from this slide. One is that this is a special case of Boolean satisfiability, in that this is one kind of a circuit, and it looks like this. And the form it has is, this circuit is basically an AND of a bunch of clauses, and each clause has exactly like 3 variables or their negations. Okay. And you're not allowed to have like xi or xi bar, because you know that xi or xi bar is always true, so you will just remove that clause. So you have 3 different variables. Okay. So this is 3-sat. So yeah, so I don't think I'll be able to finish today, so I will take the first 15 minutes of the next lecture also. But the one thing I would like to say is that it should be trivial that 3-sat reduces to Boolean satisfiability. Why is this trivial? Yeah, so this is 3-sat is a special case of Boolean sat, as I told you. So this is just trivial, right? So this is so the other way around also turns out to be true. And this also is not too hard. Okay, so can you guys see how you could transform any circuit into something that has like a bunch of clauses? At least if you had let's say circuits that have only 2 inputs per gate, then can you think of a transformation?
So if we have just 2 inputs, what happens is that we can implement these k inputs with those 2 inputs gate. So for example, if we put 2 AND circuits, each of them has 2 inputs, then we can implement a p AND circuit. Or.
Yeah, I think you have the right kind of so that's true. So So what he's saying is you can think of an arbitrary circuit as just having gates that have only two inputs. So we'll do a sequence of simplification of a circuit. So to show this, you have to take some instance of Boolean sat, which is some circuit, and produce some instance of 3sat, which has like a bunch of variables and a bunch of clauses. Right? So that's what a reduction means. Into variables and clauses. And the proposition is to do this via a sequence of simplifications. And the first simplification is testing is from an arbitrary circuit to a circuit where each gate has exactly two inputs. It's like if you have an AND gate, or if it's a NOT gate, of course it only has one, but all the AND and OR gates have exactly two inputs. And this is easy because if you have an AND of a bunch of things, you can come up with an equivalent by doing some kind of a binary tree, right? Like you can take two of these guys and take the result and so on. This is so this transformation turns out to be easy. So this, let's think of it as like an easy exercise. Okay? So this is a simple thing. Question is, how can you reduce a circuit where each gate has exactly two inputs to actually a 3sat formula, right? Where you have some variables and you have some clauses.
We build the circuit of the OR gate using those case structures, right?
Right, so here you now have a circuit where every gate has exactly two inputs, right? So you still have a bunch of AND, bunch of ORs, NOTs, whatever. And these are supposed to, you are supposed to convert these into some 3sat formula which looks like this. It has some variables, it has some M clauses, each clause looks like this. Yeah, so the trick which we'll see next class, I'll spend maybe like 15 minutes of next class trying to finish this up. But so the trick turns out to be for every gate you introduce some new variable. And you ensure that that gate is computing the right answer. Okay? So it's like if, and that you can write as a bunch of ORs like this. Because now every gate has this output variable, and you try to ensure that this output variable is consistent with, the answer of this output variable is consistent with the two inputs that go in. This turns out you can write it as a 3-set formula. Do that for every gate and AND them together. Yeah, we'll see that.